Welcome everyone to The Explainer. I am absolutely thrilled to have you here with me today. Get ready, because today we are officially becoming data detectives. We're going to learn exactly how to look at a massive sea of numbers and uncover the hidden stories and real-world mysteries locked inside of them. It's going to be a ton of fun, and I promise you, by the end of this, you'll be seeing the world of data in a completely new way. Let's get to it.
Okay, so here's our roadmap for today. First, we'll introduce scatter plots and lay down our basic notation. Then, we'll learn to analyze overall patterns using what I like to call the big three features. We'll look at exceptions like clusters and outliers, and then walk through a fully worked example together. After that, we'll tackle the single most important rule in all of statistics, the difference between association and causation. And finally, we'll wrap up with a quick recap and a final challenge just for you.
All right, Section 1. Intro to Scatter Plots, the detective's ultimate tool. To really analyze data like a pro, we first need to understand the tools and the visual language we're using.
So the crucial starting point here is that we have to strictly define our notation before we do anything else. When we talk about scatter plots, we are dealing with bivariate data. Break that down. Bi meaning two, and variate meaning variables. Basically, we're just looking at the relationship between two different things. Now, we always use the x variable for our independent data. That's the one that runs along the horizontal axis at the bottom. And we use the y variable for our dependent data, which runs up and down the vertical axis. Getting this x and y notation straight in your head right now is absolutely the key that unlocks everything else we're going to do today.
Moving right into Section 2, analyzing the overall pattern, the big three features. Now that we have our grid and our variables locked in, how do we actually read these visual clues?
Well, we do it by looking at the overall pattern. Whenever you look at a scatter plot, I want you to train your brain to look for the big three features. Number one is direction. Are the points generally trending upwards, which is positive, or are they trending downwards, which is negative? Number two is form. Do the points look like they're following a straight path? If so, they're linear. If there's a clear curve to them, they're nonlinear. And number three is strength. Are the points packed super tightly together around that imaginary path, meaning it's a strong association, or are they scattered far apart, making it a weak one?
All right, detectives, time for our first pause check. Imagine you look at a scatter plot and notice that high values of the x variable occur with low values of the y variable. Is that direction positive or negative? Actually, just take a second, pause, and really think about it.
Okay, do you have your answer? It's negative. Think about it like a seesaw. If you picture the graph, as you move to the right, meaning that x value is getting higher, the points are dropping down, meaning y is getting lower. That downward slope, where one goes up and the other goes down, always indicates a negative direction. Fantastic job if you caught that.
Let's jump to Section 3, clusters and outliers, deviations from the pattern. Because here's a little secret about real-world data. It is almost never perfectly neat. We have to be on the lookout for deviations. And honestly, these deviations are just as important as the main pattern itself. Sometimes you'll spot an outlier. This is an extreme value that sits way out there, far away from the rest of the pack. It's the rebel data point, and it usually means something highly unique or unusual happened right there. On the flip side, you might see a cluster. That's a specific group of data points heavily concentrated together in one tight little huddle on the graph. Spotting these clusters and outliers, that's where you start uncovering the really incredible hidden stories inside your data. Let's move on to Section 4, a fully worked example, Amelia's basketball practice. It's time to put all of these detective skills to the test with a real-world mystery from our source material. Does practicing a jump shot actually improve your basketball game? Let's figure it out. This data perfectly illustrates our concept. Let's look at Amelia's bivariate data, and notice how we are strictly defining those variables again. Our independent x variable is the number of hours Amelia spends practicing her jump shot. Our dependent y variable is the number of points she scores in an actual game. Just look at the numbers. When x is 5 hours, y is 15 points. When x goes all the way up to 12 hours, y jumps up to a massive 36 points.
So, let's mentally walk through our analysis steps as data detectives. Step 1, we plot the x and y data points on our coordinate plane. You can imagine putting a dot at x equals 5 and y equals 15, and keeping that going for all the rows. For step 2, we check for direction. What are we seeing? Well, high x values, like those 12 hours of practice, occur with high y values, like 36 points. As one goes up, the other goes up. And for step 3, checking for form and strength.
If we map those points out in our heads, they follow a very clear, tight, straight path marching upwards.
Bringing the whole shebang together, we can confidently summarize Amelia's data. The direction? Positive. The form? It's linear, because those points would form a relatively straight line. The strength? Very strong, because the points are packed tightly around that imaginary line of best fit. And finally, if we look for deviations, there are no extreme values or obvious outliers here. It is literally a textbook example of a strong, positive, linear association. Bottom line, Amelia's practice is absolutely paying off.
All right, Section 5, Association versus Causation, the golden rule of statistics. I need everybody listening to pay super close attention right now, because making a mistake on this next concept is hands down the most common error people make in data analysis.
We have to talk about the difference between association and causation. An association simply means that two variables happen to move together in a pattern. Amelia's practice hours and game points move together, right? But causation is a much heavier claim. Causation means that a change in one variable actually makes the change in the other variable happen. They are not the same thing. Just because two things move together on a graph does not mean one is the boss of the other.
Which brings us to the golden rule of statistics. Say it with me. Correlation does not prove causation. As data detectives, you have to promise me right now, you will never claim that an association proves one thing caused another, just because they look linked on a scatterplot. There could be an entirely different, hidden reason for the pattern. Let's put that to the test right now with our second pause check. Imagine a scatter plot showing a strong, positive, linear association between an elementary student's shoe size, that's our X variable, and their reading level, our Y variable. As shoe size goes up, reading level goes up. So does a larger foot actually cause better reading? Pause for a second and think about how you'd explain this using our golden rule.
And the answer is absolutely not. Having a bigger foot doesn't magically inject reading comprehension into your brain. What's really happening here is that a hidden variable, in this case, the child's age, is causing both the shoe size to get bigger and the reading level to improve. The shoe size and reading level are associated, yes, but one definitely doesn't cause the other. This perfectly proves why we never ever assume causation just by glancing at a scatterplot.
Moving to Section 6, Recap and Transfer Question. Your next data mystery. You guys are doing fantastic. It's time to quickly wrap up our explainer and review everything before I hand off your final data mystery.
Let's rapidly review our cognitive map for today. We learned to strictly define our bivariate data, using X for the independent variable and Y for the dependent variable. We trained our eyes to analyze the big three: direction, form, and strength. We kept on the lookout for deviations, like those sneaky clusters and outliers. And most importantly, we learned the golden rule: association does not prove causation. Now I want to leave you with one final set of source data. Here we have a table tracking young children. Our X variable is the child's age in years, and our Y variable is their vocabulary size, basically the number of words they know. At age 3, it's 655 words. By age 7, it's ballooned up to a massive 3,195 words. So here is your transfer question to solve completely on your own. Based on the data in this table, what are the direction and form of the association? And crucially, keeping that golden rule top of mind, does this data strictly prove that just getting older causes you to know more words? Or might there be other factors at play? I'm going to leave you to ponder that mystery using your brand new data detective skills. Thank you so much for joining me in this explainer today. Keep asking great questions about the data you see out there in the real world, and I will catch you next time.